Okay, so for the first chapter, I don't you go off the books chapter that we're supposed to be doing. I don't think it goes into the material that we're going over very well. So what I like to do is I like to supplement the first chapter for my chapter 1 for my Cisco course, which is a basic introduction to networking. We're going to talk about basically how different types of networks are used in our everyday life, how the different topologies and devices work within businesses, to talk about the characteristics and explain trends in networking in general. We're going to talk about specifically how the world is globally connected, WANs, the internet, the networking as a platform, and changing a networking environment. This is a big one because here, like we talk about LANs and WANs and the internet, but as we start talking about the changing environment, that's when we start talking about our PANs, our private area networks, or our campus area networks. And then we'll end with a summary. So globally connected. One of the nice things about our technology is it allows us to connect people, devices, information, and data from all around the world. Great example. I just found out yesterday, 5 minutes after it happened, that China had an outbreak of bubonic plague. I mean, literally, China quarantined a city of 130,000 people, and within minutes, the rest of the world knew about it. And that's actually a big part of that is tied directly to our technology, our networking, our communication. So one of the pros is good communication. However, one of the bad is now we're all kind of interconnected with one another. And that's always kind of an iffy thing. So with this chart, the different eras, fixed computing, BIOBAD, Internet of Things, and Internet of Everything, you'll notice right now we're in the Internet of Things. We've transitioned out of the mobility and bring your own device type thing, and essentially we are in the age of devices. We actually have more devices, not computers, not laptops, other devices connecting to the internet. And right now we have about 10 billion total items connecting to the internet. And that's kind of a lot considering our population right now isn't 10 billion. It's actually around about 7 billion. And even that, even like half of them have internet. That's a far stretch too, saying that half the people on the globe have internet. It's probably a lot less than that. But statistics have shown that we are actually moving to almost having 50 billion devices connected to the internet by the end of 2020. Another pro for our networking communication is we can actually now have a global community. I view this as negative, but it's also some positive as well. One of the positive is you can actually now hold meetings and not have to be in the same physical location anymore. You can now actually be in a virtual environment. And actually, even with this course, we're starting to see more of a virtual learning environment popping up as opposed to a traditional one. So how does networking impact our daily lives? It changes the way that we learn, communicate, work, play, pay bills, and relax. Actually, the way we learn. 20 years ago, this would not have been viable. The way that we communicate. Look at what we had 12 years ago, or 13 years ago, or 20 years ago. I don't know if many people remember, but we used to have pagers. Then we kind of transitioned away from pagers into cell phones. Now cell phones are pretty standard. I mean, that's something that pretty much every person, at least semi-adult, 12 and above, at least has or had access to. Changes the way that we work. Again, no longer are we tied to a physical location. A great example. I'm the instructor for this course. I could be traveling. I could be out of the country. Doesn't matter where I'm at. But I can still do my job as long as I have internet access. The way that we play, online gaming has increased dramatically. The way that we pay bills. I actually have no bill that comes in a papered form. Everything that I deal with is all electronic based. Again, pros and cons for that, but I mean in general, it kind of does make my life a lot easier. But one of the issues is there is no one size fits all. We have many sizes of networks, and that comes from small networks, a few PCs, maybe a PC, or maybe a few devices, to a small home office, which might connect a few PCs. More than one, but less than, 20-ish. Versus a medium to large business. And that could be anywhere between a few hundred PCs, several thousand PCs. It varies. And then worldwide, obviously, would be all smaller networks connected to a larger network, and then brought into some type of hierarchy. And if you think about the internet, it's actually just a large collection of other networks that are all networked together. So what's the purpose of the network? And a big part of the purpose is actually sharing resources. And we can share resources one of two ways. Normally, client-server is the first way, and that is where we have a server or a dedicated device hosting a resource, regardless of what it is. If we're looking at the top left, we have one browser computer, and he's browsing resources from each of these servers. Bottom right, we actually have one server with multiple PCs browsing to it. So I mean, client and servers, again, subjective, but again, who has the resource that you're trying to access? And so this is one of our major ones, versus peer-to-peer, which is everyone sharing resources. And so there is no centralized management, there is no centralized communication, it's just, I have this, you have that, let's share, and we share. Though it's less complex, but it's a lot less secure. And it's not scalable. That means that it's hard to grow. So moving past this would be our LANs and WANs and the internet. Again, a LAN is just a local area connection. A WAN is a wide area connection. But what does that really mean? How does this compare to like VLANs or PANs or CANs? So a LAN is just a local area network or a shared common network for resources. A VLAN is the same thing. It's just a virtual LAN, and it's actually used to scale out the access to common resources. So with that, what's a WAN? A WAN is just a large collection of LANs. So what would the internet be? The internet is just a large collection of WANs. So how do we actually wire up our LANs and WANs? So in the top diagram, we have two LANs and an inner network. So our WAN is in the middle, and we have devices in each of the LANs. Our WAN actually connects both of those LANs. Now this can be devices and media and services. All of these make up the different components of a network. Devices are in devices, computers, networks, phone services. Media is the actual physical wiring or wireless. Last is services, policies, procedures, standards, rules. How are we communicating, or what are we communicating? Again, other end devices could be all different types of workstations, or laptops, or servers, printers, or endpoints, or cameras, mobile devices. I mean, end devices are so just broad. So, we already talked about our media, we already talked about our services, we already talked about our end devices. What about the portion that's in our interconnect? And that can be any of our hardware. That's our routers, our switches, the things that actually allow us to connect our physical media. So what are some of our physical medias? There are three major types: copper, fiber, wireless. Copper is actually copper-based. That means the core of the cable is copper. That means it actually transmits in electrical impulses. Don't worry about this so much, because we actually have a dedicated lecture just on our cables. Next would be our fiber, which again is just plastic or glass polymer, or plastic polymer or glass, and that actually transmits light. Last would be frequencies or radio waves or waveforms in some way. Could be cellular data or radio frequency or Bluetooth or different types of waves. So how do we actually represent this? So our end devices, again, desktops, laptops, printers, phones. Intermediary devices, those are the devices that connect our equipment, our routers, our LANs, our other devices, and then our actual media. Wireless is a wave. LAN is a solid line. Our WAN is actually a lightning bolt. Why do we care about any of this? Big part of that is so that when we do diagrams, we can use the right type of key. We can make sure that when we talk about our LAN, we have the correct cable. So we've already talked about the two most common infrastructure types, LANs and WANs. But what about a MAN or a wireless LAN or SAN? So MAN is actually just a metro area network, and that's just like citywide. So I mean, how big does it have to be before it's a wide area network? Or how small does it have to be before it's a local area network? These are all conceptual. A LAN just allows you to locally share resources. Locally could be a pretty good size. A WAN, same thing. A MAN, same thing. So why do we denote wireless LAN as a WLAN? I thought a LAN was just a LAN. Well, a LAN is a LAN, regardless if it's a virtual LAN or a wireless LAN. It's all the same thing. It's just we like to categorize and classify it. Yeah. Next, storage area network, a SAN. This is just a high-speed LAN that acts as a dedicated local area connection for the purpose of storage. A simple LAN, again, is just individual devices connected to a switch, all sharing the same resources. Again, a LAN, and now we're actually connecting two LANs by a WAN. Lastly, the internet. The internet is just a large collection of LANs that make up WANs, and a large collection of WANs. So now let's talk about the internet versus extranet versus intranet, which is different than the internet. So intranet means inside only, so it could be just a company-only network. Extranet could actually be the customers directly that the company deals with. Not everyone, but just, directly dealing with people that deal with the company. Lastly would be the internet, which that would mean everybody. So how do we connect people, devices, to the internet? Big part of this is actually covered in another chapter, but here we cover basic internet speed with DSL or cable or broadband versus cellular or satellite or dial-up. All of these connect us to our internet service providers, and then from our internet service providers out to the internet. Same thing with businesses. So now let's talk about networking as a platform. This is one big thing that we don't always get to discuss, but I think this is really important. This is our converged network. And that is before we had 3 separate networks. We had a data network, we had a voice network, then we had a broadcast network, or TV network. But we've actually converged everything to one single network. And we can actually segment or separate our network using VLANs so that all of these networks can remain separate but still using the same connection or connections. Again, this is our data, voice, video. If you ever think about broadband, Cox, Comcast, anyone that has AT&T, Uverse, or any of the major broadband providers, they actually on one cable provide data, phone, video. All this really allows us to do is kind of take one network, one physical media, and actually start building upon that. And we're actually bringing the world closer together. Going back with online gaming or video conferencing, news, videos. Again, right after China closed down or quarantined 130,000 people, the rest of the world knew within minutes. That's a huge thing. So, what supports our network? Because we talk about networks, but what are services or what are things that support our network? And that's actually our fault tolerance, scalability, quality of service, and security. These are just 4 of the major ones. Not the only 4, but just 4 major ones. Fault tolerance is actually if a component of our network fails, can we actually get the information back to the other side? And the way that it works now within our packet switch networks, yes, if any one device fails, we can still allow communication between other devices. Next, scalable. We actually have 3 tiers of ISPs, Tier 1, Tier 2, Tier 3. Our Tier 3 are what's known as our local ISPs. Basically, when you connect to your ISP, you have to go through their network to connect to the Tier 2 provider. The Tier 2 provider doesn't directly connect to the internet. that they connect to a Tier 1 provider. Only the Tier 1 providers connect to what we know as the Internet. And in all reality, the Internet is just really a large collection of all our Tier 1 providers. That's it. Now those Tier 1 providers consist of multiple Tier 2 providers and a bajillion local ISPs or Tier 3 providers, but it's this hierarchy that allows us to be flexible, to grow, to expand as we need, and to keep up with that growth. Next, providing quality of service. So this is a big one. Because we're taking our data, our voice, our video, and putting it on the data network, how do we make sure that things that are real time have higher priority? For example, voice or video. Is that more important than data? I mean, if your web page takes an extra second, is that really that big of a deal as opposed to your voice, your phone call being a second out of sync? The voice phone call could be a huge issue. The web page, not so much. Lastly, networking security. And that is actually just protecting the way that we live, the way we learn, play, and our work. And that's done through encryption, our policies, our equipment, and that keeps things out like identity theft and criminals and cheaters and competitors and fraudsters. Fraud people. So the last major section of this is actually our changing environment. And that is actually us moving to a BYOD, online collaboration, video, and cloud computing. So what is BYOD? And that's actually just a concept of us bringing our devices to the network. That's it. No longer having to be tied to what the company has, but us using our tablets, our notebooks, our smartphones, things like that. Next, online collaboration. No longer having to be in one area. We can actually now be in multiple areas and still collaborate, whether it's through messaging or online conferencing or voice or telepresence or telecommuting, or just done through smart applications. All of this is changing the way that we collaborate with one another. Instead of having a on-site, we can now do it from wherever we're at. So we can actually now call up people in Asia or Germany or France and get them on a sales or a design team meeting. No longer do they all have to be tied in the same location. So here's a big thing for video communication. Early 2000s, we had 250-ish million. 2012, we had 2 billion. And notice, while our world population has increased, our internet users are actually increasing faster. So what's cloud computing? Cloud computing is essentially just taking equipment or services or devices and sticking them in the cloud. But what's the cloud? The cloud is just a clever way for the internet. And this is allowing us to refocus our IT, reduce costs, help actually increase deployment, and become more flexible. Great example with this is Google Docs or Microsoft OneDrive or even just Office 365. No longer does an individual have to purchase Office. they can actually now just stream off this off the internet. And that actually reduces costs significantly. Also means you don't have to worry about updating your software, because as new software updates, it all updates automatically. You don't have to manage it. Less overhead. But where is all of this cloud stuff stored? A big thing for our cloud services is they're stored in the data center, and that's actually just a large warehouse with cooling, power, and fast internet. We stick our servers there so they can always be on, always have power, always have internet, and we don't have to worry about them. They're also controlled by air conditioning or heaters or everything to keep their environmental controls optimal. Does this change the way that we deal with our home? Actually, yeah, it really does. I actually now have a home automated system in my house. I can control the vast majority of lights, start my car, lock my front door, or unlock everything from just my phone. Everything is actually stored on a cloud app. In reality, I'm just logging into a web-based portal from my provider, but it's in the cloud. Now, again, all that really means is it's on a server somewhere on the internet. Can we provide power over our Ethernet? And actually, yes, we can. We can also provide Ethernet over our power lines using a specialized Ethernet over power adapter. Same thing, we can provide power over Ethernet. That would be more for like our wireless devices, like our WAPs or our cameras. So we've already talked about our wireless. So notice this is like a huge antenna outside the house. What type of wireless might use broadband? This is actually called WiMAX, the 802.16 wireless standard. So what's really funny about this is when we switched from analog to TV, what happened to all of the analog channels? They were brought out so they could use wireless broadband. All the antennas were already all there. We just had to connect them up in a specific manner to actually allow for long-term transmission of our wireless signals. That's our WiMAX. One of the last set of major slides is our security. And our security is there to actually protect us from viruses or spyware or adware, malicious attacks or identity theft or other types of things that we don't want to have happen. So how do we mitigate all these risks? We mitigate them through antiviruses, anti-spyware, anti-maliciousware, or other types of security controls. So the last major thing we talk about is our architecture. Again, we want to blend our networks, our data centers, our collaboration all together so that we can have a modern network. That's actually it. So if you guys have any questions, please let me know. Let me know how I did, and I want to thank you guys and hope you have a great day.
So after we finish the Cisco stuff, I want to cover some basic communication components for datacom. So that's going to be things like media, encoding, transmission, modulation, connecting, and multiplexing. Granted, that's not only for datacom. It's also for telecom as well, but I'm focusing more on the datacom portion. This section is going to cover Chapter 5, which again is datacom overview. So it's again essentials, motivations, concepts, and basic subtopics. So Chapter 5 in a nutshell is the overview of datacom, which seems straightforward so far. So what does datacom actually entail? Like, how does datacom work? Like, what is it composed of? So normally datacom composed or involves transmission of data, not information, but of data. Could be of information, but normally just data. Normally, again, over a physical, tangible medium. Now that's not always true though. We could be transmitting data or information over wireless. That's not physical. It does fall under our physical media, but it's not tangible. So do keep that in mind. It's kind of weird that we always talk about our physical medias being wired and wireless, even though wireless is not a physical medium. Just one of those odd things. And of those physical medias, they can be transported over current, electricity, light, fiber, and any other form of electromagnetic radiation. The information is digitized, so basically it makes it into a digital format so that it can be sent over our wire. Again, the wire, I'm just going to subjectively say, is both wired and wireless. So why does it have to be digitized? If it's not digitized, it's still going to be analog, and analog transmissions aren't where we're at anymore. We've switched everything to digital just because they're more reliable, they can be transmitted further and faster. So the essence of our data communications, it's the combination of physics, engineering, and mathematics, and where they all collide, that's where we're defining our datacom. So the motivation and scope of the subject. There are three main ideas, and that's going to be our source information. Again, that's going to be source and destination, not just source, but I mean our sourcing information. Where we're going. The transmission speed, or transmission. Not just so much the speed, but what route, what path is it going to take to get there? How is it going to get there? How do we guarantee that it's going to get there? Do we have to guarantee it's going to get there? Those are all portions of transmission. What happens if we're doing it with a shared transmission medium? Can we have multiple sources? Can those multiple sources go to multiple destinations? Can we share it? Does it have to be shared? Can it be isolated? Pros and cons for both? Those are just some of the topics that we will have to eventually discuss. The second major point is, what about natural phenomenons? If we're transmitting over electrical current, that's natural. Can we manipulate that? What happens if we do manipulate that? Are there any things that can further change it? Like outside radiation, outside noise, things that we don't want to interfere with our communication? Sure, definitely. So what are some other underlying issues? Again, types of media that are out there, and the cost of them, the pros and cons of each of them, the properties of them, the physical phenomenon for the transmission of data over them. That goes back to copper versus fiber, because copper is more susceptible to noise, where fiber is not, but fiber is more expensive. So sometimes by understanding the properties and the physical phenomenons, you can figure out which one that you want to do. Other physical symptoms or other physical issues with that particular type of cable, and problems that can arise during transmission. That's a big one. If we're transmitting multiple miles, can copper go that far? Some copper yes, some copper no. In general though, copper doesn't go that far, so that's a problem that you'd have to consider. Sharing. If we only have one infrastructure, if we only have one medium, how do we share it? Can we share it? Do we have to share it? All good questions. That's actually a major point for our multiplexing, because that's one way that we actually do share medium. We'll cover that more towards the end of this slide, and definitely within further chapters. So, let's talk about if we have multiple sources, and they each need to go to a different sender. So how do we actually get a system that does that? Well, what ends up happening is we break it up into several different subsections. The gather, prepare, transmit, extract, deliver. Same thing like when you mail a package. If you're on the East Coast and you want to mail packages to the West Coast, you gather all the packages going to the West Coast. You prepare them. You actually then ship them. Once you get to the West Coast, even if they're going to all different sections of the West Coast, they all get kind of packaged together, then shipped out. That way you're not having to ship out individual. You're just shipping out one big block. Once it gets there, you extract the different packages to wherever they need to go. Some packages may be going to the south, some may be going to the north, some may be going to central. Just kind of depends. And then you deliver them to their individual locations. Graphical representation of that is you prepare it, you send it over the medium, you extract it, then it gets delivered. Each one gets prepared, transmitted over one medium, gets delivered, and extracted at their specific location. What happens if there's errors? We have to provide some type of error correction, but again, we're going to cover that at a later date. It's a lot more complex than that, but I mean, in essence, that's what we're talking about. Here we go. This is our nice, lovely, complex topic. Information. We encode it. We encrypt it if need be. Then we actually encode it on a channel, and we send it to a multiplexer. It gets modulated, gets sent over the wire, it's demodulated, decoded, de-encrypted, and received by the sender, or received by the destination. I mean, even this is kind of simplistic as well, but the thing here is to recognize if we have information, we have to encode it, maybe encrypt it, and send it out. But we're going to be sending it out with multiple connections. And then there's a system in place that will actually multiply it, or modulate it via multiplexer, so that we can share one wire. A great example is like when you get on the internet. Not all of the bandwidth on your home computer is going to just one location. It's actually being combined and sent over that one wire so that you have multiple connections. Again, this is just a concept framework, so it's not concrete. If we're talking about just processing at the sender end, that's the top portion. Information, encode, encrypt, multiplexer, modulate, and then it gets pushed out. On the other end, on the processing the receiver end, it comes in on the wire, gets demodulated, and then resent to the individual destinations. So that's actually about it for Chapter 5. So other areas we're going to talk about will be in later chapters. It's going to be our analog, our digital, characteristics, phases for our multipliers, our multiplexing, amplitude, frequency, phases, encoding, decoding, compression. But there's a few more items that I do want to make sure that we cover, just so that we have a nice understanding. Encrypt versus decrypt. So encrypt is where you take data and you actually can make it private. You can scramble it so that it has to be decrypted. Basically, it makes it only readable for those that have a key to descrambling it. For channel encoding, decoding, that codes it to a channel, and part of that coding to a channel allows for correction. It normally does correction via parity or checksum. Multiplexing versus demultiplexing. So if we have a shared wire, multiplexing is the ability that we have that will put it on a wire, and we can share that wire. Essentially, we take turns. Modulation versus demodulation. That's how we manipulate the electromagnetic radiation. Physical channels. That's our physical medias. Copper, fiber, wireless. How do we send that data? In what type of mode? Are we sending it via serial? Are we sending it via parallel? That's a good question to answer. What's serial? What's parallel? What's our bandwidth? What's our capacity? What's our noise? Those are all major topics we'll be discussing in later chapters. That's it for Chapter 5. Thank you. Chapter 6, Information Sources and Signals. So, some of the major topics we're covering is sources, analog, digital, periodic, aperiodic, sine wave, half-life math, time and frequency domain representations, bandwidth, baud rates per second, conversions, bandwidth for digital, synchronous line coding, all the way up to 6.20. Now, you have to remember that within our individual chapters, they're not always... We have certain objectives for each week. And so what I'm doing is I'm lecturing on each of the PowerPoints for the chapters that were assigned reading for each week. So I'm trying to do one set of slides that hit on the core topic, and then the required PowerPoints. So, we're going to dive more into a greater detail for Datacom. After this chapter, you should be able to at least have a basic understanding of what Datacom is. So, our communication system should be able to accept input from one or more sources and deliver it to specific destinations. Now, that could be done through a shared medium or a non-shared medium. So that basically one wire, we can all share it, or we can have individual connections. Realistically, we're talking about shared medias because we don't want to have a cable from our computer to every other computer, or from our phone to every other phone. It's just no longer realistic. We want one medium between us and everyone else, and we want to be able to share that one medium. So if we're using like the internet, for example, our source versus destination, our computer and a web server. You want to go to Google. You go to your web browser, type google.com, hit enter. Our computer is the source. Google is the destination. Google actually returns to us the web page. So I mean, that's what we're talking about when we say information sources. So analog versus digital. So what is the difference? One of the big things with analog is it's a never simulated size, or it's a never simulated item, which means you always know exactly what it is. Think of an analog clock. As it goes around the clock face, you always know exactly what time it is, what second is, because there is no sampling. With digital samples, they sample several times a second normally, if not more, and it's a fixed set at that precise moment. So it samples. Another way to look at this is our analog and digital signals. Normally our analog is not square, because again, it's never a realistic expectation. So we're looking at the very first between 0 and 1. Here, for our analog, 0 through 1, what number is that? Is that a 1? Is it kind of going to a 1? In digital, it's either 1 or not. So within our sampling, we just set it to 1. Even though realistically, it didn't start out as a 1, it's kind of going to 1. But halfway through 1, it becomes 1. But I mean, on average, it's a 1. So, periodic versus aperiodic signaling. Aperiodic is just the reverse of periodic. And that is a time interval over time. Normally that doesn't repeat. Sine waves, everything within electronics, we deal with sine waves. You never get away from the math. It oscillates. What do I mean by oscillates? Goes up and down. That's what I mean by oscillate. Amplitude, if here is our common, our amplitude is actually the height of the wave. A frequency, one of the big things is our wavelength. So a wavelength is actually one wave before it starts repeating. Like here it starts repeating. So here's a wave. Here's another wave. Here's another wave. So, I'm sorry, I forgot to say frequency. Frequency is the number of oscillations per a given moment in time. So let's say we're looking between 0 and the third slash. It actually goes through 1.5 waves. So, or 1.5 oscillations. If we're looking at that time. If we're looking at the entire time bar, 1, 2, almost 3. Phases is another big one. Is how far from the start of the sine wave is shifted reference in time. Like we start going up, and then it shifts so it goes back up. That could be a shift. So, frequency, amplitude, phase, wavelength. Those are our major ones. So let's see this in a little bit better graphical way. Our original sine wave, assuming 1 second, 2 second. So let's say we want to increase our frequency. That becomes the next one. Notice here is still our 1 second, but we're now doing twice as much in 1 second. Let's say we want to lower the amplitude. Again, you notice the signal is no longer as strong, but we're actually able to do 1 in 1 second. What happens if we want to change the shift? Notice this is our original. It actually swaps it. It inverses it. So instead of going up, it goes down. They all have their functions. It just depends on what type of multiplexing and what type of characteristics for the media that we're looking at. So this helps build a nice solid foundation. So how do we measure this? We measure it in hertz. Normally a hertz is how many waves per second. So here we're looking at if t is 0.5 seconds, 1 divided by t or time, we have 2 hertz per second. Okay, 1 divided by t T is our time. T would be the amount of seconds it takes for a complete cycle to go through. And yeah. So what happens if we have lots of hertz? At what point does it go to megahertz, or kilohertz, or gigahertz, or terahertz? So normally our frequency, it's all metric, so it's all base 10. So kilohertz, or hertz is our base, and kilohertz for every 1,000 hertz. For every 1,000 kilohertz, it's a megahertz. For every 1,000 megahertz, it's a gigahertz. For every 1,000 gigahertz, it's a terahertz. They're increasing by thousands. So far, we've been looking at pretty simple signals. Those are just, again, simple. Now let's look at some composite. Those are complex signals. Here is our simple. Here's another representation of simple. Here is a composite signal. It doesn't quite follow a straight sine wave. So it's a composite signal. Composite just means complex. You'll notice as it goes up, it may shift here for a second, and go back down, loop back around, shift again, and repeat. The importance of our composite signals is it's not always about a straight sine wave. We have to worry about modulating it and demodulating it. That way we can add additional data on it. So it's not just strictly a pure sine wave. So there have been several methods invented to represent a composite signal. One of the big ones is our frequency domain, our time domain, our amplitude domain, and a few other types of domains that we'll get into when we talk about multiplexing. But the first one I want to really talk about is our time and frequency. Our time, or frequency in hertz, and the actual amplitude. You start noticing this is more looking like a digital signal. And there we go. A time and frequency domain can also be represented as non-periodic signals. So that's just an item to throw out there for you guys to know. Bandwidth. So what is bandwidth? Bandwidth normally is the amount of data that a signal can carry, normally minus the overhead. So how do we look at the bandwidth of an analog signal over a given period of time? Because analog fluctuates. How does that differ from digital? Digital does fluctuate, but not as bad. Normally digital, there's two states, on, off, or 0 and 1. So it's on or off. There is no in the middle. Here, if we start talking about 16 bits, you start seeing middle steps. That really isn't a middle step. It's here we're representing a 1 as a +5. So here it's a +5 and +0. So instead of doing like a half line halfway through a number, they just did it this way. So instead of it being +5, +5, +5, 0, they just kind of compromised and put it halfway. So the different levels of our numberings, it's just kind of depending on how many bits we're doing. Normally we don't do 2 bits like that, we do them individually. So it's more like this. Every number is calculated. We don't normally double step them like this. So bauds and bits. How much data can be sent at a given time? Now remember, that's data and there's still overhead for sending it. So you have to make sure we think about that. the rate at which the data can be sent, it's reliant on how many signals, how much time, how much error, how big of chunks. So it's not just one area. There are several that we have to think about. With our hardware, how fast can our hardware send it? Does both sides accept the measure of communication over the time? How many times the signal changes per second is normally defined as a baud. So if the signal can change 1,000 times a second, it's 1,000 baud. Which we don't normally use the word baud anymore. Early communications, late 90s, early 2000s, they were very big with baud. Now, not so much. So how do we actually calculate it? And that is bits per second is equal to how many bauds times log 2 of the number of levels. How many levels do we have? Let's say we have 1,000 baud and we have 4 signal levels. 1,000 baud times log 2 of 4. I'm not going to do the calculation for you. This isn't math. I just wanted to show you that there is a math behind this and that there's the importance of having it there. So how do we convert analog to digital and digital to analog? That's a big one. We do approximations. Here we have digital signal A, and let's look at the same analog signal on B. They can represent the same signal, but at the same time, so can C and D. So there is some conversion loss when we convert digital to analog and analog to digital, because they're approximations. I know that I skipped a few slides, but it was just getting kind of repetitive. One major one that I did want to discuss was analog to digital conversion, because we talked about sampling before. So what we do is we sample an analog signal at a specific rate. It could be 30 times a second. And what we do is we quantify it. Then we encode it. That allows us to have our digital signal. That is sampling. Sampling is, again, looking at what the rate is at a given point in time. We quantify it, then we encode it. But how do we see that in a graphical representation? Here we go. At that given time, we rank it. That given time, we rank it. And we actually only look at those times. If we want a better representation, we sample more. The more that we sample, the better representation of the analog signal we get. We do the same thing with voice. We sample. The last one was, how do we sample a digitized voice call? So there is a representation. Normally we're sampling it, how many samples times how many seconds, times 1,000 or 8,000, and that will be grouped by another multiplication of 8 times how many bits per sample. So if we are looking at 60 samples per second, so 60 samples every 1 second times, there are 8 bits that we're sampling per sample. That would be 8 divided by 60. We could have our communication. There's just a lot of data there. Through cross cancellation, we can actually just do 64,000 times 8 bits divided by however many seconds. And that's pretty much Chapter 6 in a nutshell. Okay, so I wanted to discuss some follow-up items. One of the first things is our APA formatting and citation. That goes for both our IPs and our discussions. Remember that we have to do all of our work according to the APA manual. So if you're not sure how to do that, go online. You can type in APA formatting. If you don't want to look it up online, you can go to any of the tutorial services. We have a writing, we have a library service. They can give you additional resources on how to do APA formatting. That's important. That's not going away. In discussions, same thing. We have to be doing our citations in our discussions, because one of the big things is, for our citations, we're building off of other people's works. So it's a way for us to verify what we're claiming is supported by the literature. So when I say something at the sky is blue, you can take my word for it, or if I provide a citation, you can take an expert's word for it, and then I built off of that. So it just kind of increases your credibility. We should be at least citing in every post, or as much as possible, because again, we're trying to link what we've done back to the literature. Same thing in our IPs. Every paragraph should be tied to a source. Every paragraph is an idea, and every idea we need to have support within the literature. And I know at this level it's not that big of an issue, but you want to get in the habit of doing that, so when you start doing higher level work, it's second nature. Also, length. We don't need posts that are great job. I mean, don't get me wrong, it does add to it, but when I start grading for posts, I'm not doing full credit for those that have 3 posts and 2 of them are great jobs. I don't count the great jobs as a post. For our discussion board, I'm looking for 3 solid responses with citations. For our papers, I'm looking for 3 pages of content with citations. So what I mean by content is, that's 3 papers on topic. That's not a cover page, that's not your reference page, that's 3 content pages. 2 if you're really good, but I'm really looking for 3 if you're doing diagrams. Diagrams totally are okay, as long as you're doing them within APA formatting. Lastly, grading. Again, I grade heavily off of attempt, like if you're putting an effort into it. Like if you did 2 pages and you did a few citations, and I could see that you were making an effort, I'll meet you. But if you post once, or you did a page and a half with 1 citation, that really isn't you making an effort. If you get stuck, don't get me wrong, some people a page is a lot. If you get stuck, you have plenty of resources to bolster up your paper. You can contact me, I'll help you. If you don't want to contact me, we have a writing center, we have a tutorial center, we have plenty of help for you to get. If you need tutoring, there's a lot of tutoring out there. And again, provided from the school. All you have to do is say something. For our tutorial lab, we have tutorial services for SQL, we have tutorial services for database, we have tutorial services for math, English, writing, research, library services. I mean, we have a great amount of tutorial services. And if we don't offer tutoring in a specific area, you can ask for it specifically, and they will find tutors for you. So you could not get tutoring because you can. If you ask for help, the school will get it. If you cannot get it from the school, there's other help. I will sit down with you. I will do as much as I can with you. If you need one-on-one, if you need tutoring and you don't get tutoring, that's not a failure on my part. That's not a failure on the school's part. That's only a failure on your part, because there's plenty of opportunities there. You have my number. You have my email. You have 2 emails from me. You have my cell phone number. You have plenty of ways to get a hold of me if you need help. And again, if you don't capitalize on help and you need help, that's on you. Because there's plenty of help out there. all you have to do is say something. Thank you.